Hello everyone, I am Sushmita of BSc 3rd year 5th semester of Isabella Thoburn College, Lucknow, and my college roll number is 205036, and I am here with the topic linear transformations. Now here's an introduction to linear transformations. Here we suppose a function t that maps a vector space in V into a vector space capital W. Here we can see that T is such that V is a vector space which is mapping into a vector space capital W. Here V and capital W are the vector spaces, and V is the domain of T and W is the codomain of T, and here R is the range of the function. Now what is the image of V under T? So if V is in capital V and W is in capital W such that T of V is equals to W, then W is called the image of V under T. Now what is the range of T? So the set of all images of vectors in V is called the range of T. Now what is the pre-image of W? So the set of all V in capital V such that T of V is equals to W, this is called the pre-image of W. Now here's an example that a function from R square into R square. So we will suppose a function t such that R square is mapping into R square. So V is equals to V1 comma V2 which belongs to R square. Now T of V1 comma V2 will be equals to V1 minus V2 comma V1 plus 2V2. Now first we have to find the image of V is equals to minus 1 comma 2, and second we have to find the pre-image of W is equals to minus 1 comma 11. Now here's a solution of the example. So first we have to find the image of V is equals to minus 1 comma 2. So this implies T of V is equals to T of minus 1 comma 2, which is equals to minus 1 minus 2 comma minus 1 plus 2 into 2. So this is equals to minus 3 comma 3. So this is the image of V is equals to minus 1 comma 2. Now second we have to find the pre-image of W is equals to minus 1 comma 11. So T of V1 comma V2 will be equals to V1 minus V2 comma V1 plus 2V2. So it will be equal to minus 1 comma 11. So this implies V1 minus V2 is equals to minus 1 and V1 plus 2V2 is equals to 11. So this implies V1 is equals to 3 and V2 is equals to 4. Thus 3 comma 4 is the pre-image of W is equals to minus 1 comma 11. Now linear transformation. So here are the two axioms of linear transformation. First is T of U plus V is equals to T of U plus T of V for all U comma V belongs to capital V. Now second is TCU is equals to C T of U for all C belongs to capital R. Now a linear transformation is said to be operation preserving because T of U plus V is equals to T of U plus T of V, and T of CU is equals to C into T of U. Here T of U plus V is the addition in V, and T of U plus T of V is addition in W, and T of CU is the scalar multiplication in V, and C into T of U is the scalar multiplication in capital W. Now second is a linear transformation T such that V to V from a vector space into itself is called a linear operator. Now example 2 is verifying a linear transformation T from R square into R square. So T of V1 comma V2 is equals to V1 minus V2 plus V1 plus 2V2. So here is the proof that U is equals to U1 plus U2 and V is equals to V1 plus V2 such that vector in R square C is such that any real number. So first is vector addition. So U plus V is equals to U1 comma U2 plus V1 plus V1 comma V2. So it will be equals to U1 plus V1 comma U2 plus V2. Now T of U plus V will be equals to T of U1 plus V1 comma U2 plus V2, which will be equal to U1 plus V1 minus U2 plus V2 comma U1 plus V1 plus 2 of U2 plus V2, which will be equal to U1 minus U2 plus V1 minus V2 comma U1 plus 2U2 plus V1 plus 2V2, which will be equal to U1 minus U2 comma U1 plus 2U2 plus V1 minus V2 comma V1 plus 2V2, which will be equal to T of U plus T of V. Now scalar multiplication. So Cu will be equal to C of U1 plus U2, U1 comma U2. So it will be equal to C of U1 comma C of U2. So T of Cu will be equal to T of Cu1 comma Cu2, which will be equal to Cu1 minus Cu2 comma Cu1 plus 2Cu2. So which will be equal to C of U1 minus U2 comma U1 plus 2U2. So it will be equal to C of C into T of U. So therefore T is the linear transformation. Now here is another example that functions that are not linear transformation. So here in this example I'll be telling you about the functions that are not linear transformations. So first is fx is equals to sin x. So this is not a linear transformation. How? We can see here that sine of x1 plus x2 is not equal to sine of x1 plus sine of x2. So here for an example we can see that if we put x1 is equals to pi by 2 and x2 is equals to pi by 3, so sine of pi by 2 plus pi by 3 is not equal to sine of pi by 2 plus sine of pi by 3. So in this case we can say that fx is equals to sin x is not a linear transformation. Now another is fx is equals to x square. So in this case x1 plus x2 whole square is not equal to x1 square plus x2 square. So for an example, if we put x1 is equals to 1 and x2 is equals to 2, so 1 plus 2 is equals to 3. So 3, if we do square of it, it will come as 9. Now on the right hand side, if we see that 1 square is equals to 1 and 2 square is equals to 4. So if we add 1 plus 4, it will be equal to 5. So these both of these are not equal. So in this case we can say that f of x is equals to x square is not a linear transformation. Now third is fx is equals to x plus 1. So f of x1 plus x2 is equals to x1 plus x2 plus 1. So f of x1 plus f of x2 is equals to x1 plus 1 plus x2 plus 1, which will be equal to x1 plus x2 plus 2. So f of x1 plus x2 is not equal to f of x1 plus f of x2. Here we can see that x1 plus x2 plus x1 is there for left hand side, and for right hand side here we can see x1 plus x2 plus 2 is there. So these both are not equal. So we conclude that f of x is equals to x plus 1 is not a linear transformation. Now, two uses of the term linear. Fx is equals to x plus 1 is called a linear function because its graph is a line. Second is f of x is equals to x plus 1 is not a linear transformation from a vector space R into R because it preserves neither vector addition nor scalar multiplication. Now zero transformation. So function t such that vector space V is mapping into vector space capital W. So t of V is equals to 0 for all small v belonging to capital V. Second is identity transformation. So function t such that vector space V is mapping into vector space V, means it is mapping into itself. So t of V will be equal to V for all small v belonging to capital V. Now properties of linear transformation. So function t is such that vector space V is mapping into vector space capital W. So u comma v will belong to capital V. First is t of 0 will be equal to 0. Second is t of minus v will be equal to minus of t of v. Third is t of u minus v will be equal to t of u minus t of v. Fourth is if v is equals to c1 v1 plus c2 v2 plus and so on plus cn vn, then t of v will be equal to t of c1 v1 plus c2 v2 plus and so on till cn vn. So it will be equal to c1 t of v1 plus c2 t of v2 plus and so on till cn t of vn. Now here is another example, linear transformation and basis. So let function t such that R cube, vector space R cube is mapping into R cube. It will be a linear transformation such that t of 1 comma 0 comma 0 is equal to 2 comma minus 1 comma 4, and t of 0 comma 1 comma 0 is equals to 1 comma 5 comma minus 2. T of 0 comma 0 comma 1 is equals to 0 comma 3 comma 1. So we have to find t of 2 comma 3 comma minus 2. So the solution for this example is 2 comma 3 comma minus 2 is equals to 2 of 2 into 1 comma 0 comma 0 plus 3 into 0 comma 1 comma 0 minus 2 into 0 comma 0 comma 1. So t of 2 comma 3 comma minus 2 is equals to 2 of 2 into t of 1 comma 0 comma 0 plus 3 into t 0 comma 1 comma 0 minus 2t of 0 comma 0 comma 1. So t is a linear transformation. So this is equal to 2 into 2 comma minus 1 comma 4 plus 3 into 1 comma 5 comma minus 2 and minus 2t t of 0 comma 3 comma 1. So it is equals to 7 comma 7 comma 0. So here's my references from where I have taken the content, and thank you so much for listening.